Welcome everyone, this is Ron DeMera from the University of Central Florida. Today is titled Boltzmann Machines and Spiky Neural Nets using Probabilistic Spin Logic. It's part of an SRC and Core Collaborative project in the Center for Probabilistic Spin Logic, which we call CAPSULE, that Professor Jörg Appenzeller leads as headquartered at Purdue. This work is also jointly funded by NSF E2CDA, Energy Efficient Computing from Device to Architectures program. I'd like to take a moment to acknowledge the team that we have in this project and what a wonderful collaboration it's been thus far. The overall project is a joint effort between Purdue University, University of Minnesota, UC Berkeley, and UCF since October 2017. So we're about 10 months into the first year of the project so far. There are 8 PIs from those schools and a few postdocs, plus several research assistants pitched in to create the various aspects of the work that I'm going to present today. I've color-coded those names based on the school's color scheme, and UCF's assistants are depicted here in gold color font. I especially want to recognize my exceptional PhD candidates, Ramtin Zand, who led the Boltzmann machine effort in the first half presentation today, and also Stephen Pyle, who led the spiky neuron effort in the second half of my talk. Also, our team is fortunate to have some very talented REUs funded by NSF who've done a great job supporting the project with SPICE simulations and writing some scripts. That's Adam Bush, Monica Eisinger, Michaela Payne, and Justin Sapp. So as you can see, the technical flow of the project as a whole starts with device modeling. We progress from a device to systems type of an approach. What we're going to do today is look at spin Hall effect, magnetic total junction probabilistic devices, which we call P-bit, and then use the P-bit to construct a restricted Boltzmann machine, or RBM, and then stack them into layers to create a deep belief network, or DBN. And then generalize into a simulation tool called RDBN-Sim. Then we'll mention a little bit about magnetoelectric P-bit extensions. So what are the significant contributions of this e-workshop? First, energy consumption. We achieve orders of magnitude benefit over most recent CMOS realizations by adopting a device-to-systems approach. And the idea is we're going to use integrated multiply and accumulate with thresholding operation in this P-bit based design. So today we'll quantify the energy dependence for network depth on a neuromorphic topology in terms of its number of hidden layers. Next, there's a potential to achieve significant area reductions when moving from single or double precision binary floating point representation to analog voltage levels for encoding some parts of the category and recognition information. So this provides a way to take us from thousands of MOS transistors down to just a handful by using P-bit to do this accumulate and thresholding operation in a single device. But the idea is we want to still maintain a demonstrably adequate functionality for the neuron. And last but not least, we'll take a look at the simulation framework that we've developed to give others who are conducting some design space exploration of various resistive network topologies for neuromorphic architectures, whether they be MRAM, RRAM, or otherwise. We have developed a toolkit. It starts with MATLAB. There's some Python scripts, and this integrates with SPICE, so there's simulation in the loop for the trade-off, realization, optimization, both energy and accuracy of these deep belief networks. Slide 4, research motivation. Clearly, we're in the era of big data. Last decade's advances in network connectivity and storage capacities is fueled by Moore's Law, along with popularization of social media, multimedia information collection, including image and audio data like spoken language understanding, and interconnection of databases to create data warehouses has really made cloud computing a reality. We've seen an ever-increasing need for pattern recognition and classification applications involving high-dimensional data. Clearly, these will continue to accelerate both in the server space and going forward with fog computing at the ever-expanding edge of the network. In fact, the majority, maybe 70 or 80% of digital information may spend its entire lifetime and never leave the edge of the network. That's something very new. How do we impart machine intelligence to the network edge? And do it at low energy and low area footprint, which of course equates to cost. Well, fortunately, probabilistic computing approaches have shown good classification accuracy and are generally considered promising for these type of applications. We'll examine a couple of them today. But there exists a tractability constraint, which can be overwhelming when we want to implement probabilistic computing on von Neumann computing architectures. The main limitation is that conventional fetch-to-code execute processor architectures really weren't designed for those types of applications. No matter how many of those von Neumann CPUs we throw at the problem, their interconnection cost, overhead of memory access, and exact encoding of data values is quite large compared to the classification and pattern recognition's demands. In these applications, we have high dimension matrix multiplications, and if we want to use a conventional von Neumann architecture, then we have to deal with the processor and memory bottlenecks, which may cost a lot in terms of energy and area of these address and data buses. So even though we're using GPU these days, tensor processing units, their processing and memory bottleneck is not giving us the efficiency that is either possible or that we're looking for. I'm going to focus today on deep belief networks for four main reasons. Most important for us as hardware designers is the fact that they're tractable, which means that they're going to have a straightforward architecture. Actually, we're showing in a new paper that we've submitted to IEEE Rebooting Conference that a four-state machine can be sufficient to implement the entirety of the training and evaluation steps. For instance, feed-forward state, then training to feedback state, reconstruct, update, and once all columns are updated, then we're back to a testing phase of the feed-forward state. Next, advantages include being cascadable or readily layered. For example, when implemented on a configurable fabric, which I'm a huge proponent of for their in-field adaptation to overcome troubling things like process variation or limited write endurance, besides the training process itself. Next, non-deterministic behavior. The computing elements in deep belief networks specifically give a new opportunity to leverage things like thermal noise instability in spin-based devices. And that stochasticity is a needed feature for how the computational models operate. That provides a new pathway to compute efficiently in these types of networks. With regards to unsupervised learning, from the deep learning work published by LeCun, Jeffrey Hinton, and others, towards realizing neuromorphic and other biologically inspired computing approaches has been somewhat continuous for decades, during which time many of us in the field have advanced various task partitioning, execution farming, pipelining, and clustered shared memory architectures since the late 1980s. However, trying to pluralize massive numbers of floating point operations is not the only way. And given crossbar architectures as an alternative, it could be a quantum leap to consider using post-CMOS devices for accumulation, thresholding, and especially a focus of this talk, which is to leverage the stochasticity that is both inherent and tunable in the device. In other words, leverage the intrinsic physics behavior for computation, which in previous eras, such device-inspired approaches were not fully embraced. What is a DBN? Well, deep belief networks can be composed from RBMs. RBMs have two stages, which are a visible layer and a hidden layer. The visible layer connects to the inputs, and there are unidirectional connections from visible to hidden layer. Each of the computing elements is a neuron that is going to perform a function according to this following equation. In particular, each node in the RBM has a probability to be in state 1. And the state of the node I, which is based on a logistic sigmoid function, which takes as input the connection weights between nodes I and j are multiplied and then summed across j, giving us the dot product and yielding the matrix multiplication operation. However, the most important thing for us today is that the sigmoidal activation function that we're trying to implement is computed intrinsically using the p-bit device, which is an advancement beyond previous crossbar architectures. So the RBM can be implemented by crossbar architecture, and the usual way to do that is to have a weighted array with a varying resistance that are connected to the neuron, which in this case is a p-bit that's going to perform the sigmoidal activation function. So RBMs can be stacked to form the deep belief network by having multiple layers. Depending on the dimensionality of the input data and the number of output categories, we can continue to add layers that are hidden layers from 2 up to tens of hiddens of layer, depending on the requirement. Having additional layers will elevate the recognition accuracy, but it's nonlinear in the benefit that you obtain. So one of the things we'll be talking about later in the presentation is when we add additional layers, what's the impact on recognition accuracy versus the energy cost. Next on slide 6. To utilize the hidden layers to achieve the dimensionality reduction, we apply a training mechanism. For example, contrastive divergence is a popular way to realize unsupervised learning in DBNs. It's a fairly straightforward approach. It is a feed-forward step first that we're going to apply the training vector to the visible layer, and the hidden layer H vector is sampled. Then there's a feedback step. The sampled hidden layer output is fed back, and the generated input is then sampled, yielding input vector V prime. Reconstruction step, that vector is then applied to the visible layer, and the reconstruction hidden layer is sampled then to obtain the output vector H prime. Now that we have V, V prime, and H prime, we can use the following equation to adjust the weights without even knowing the target. So in this case of unsupervised learning, we don't need to know the label and do this dimensionality reduction. So this for sure is an unsupervised learning approach. A key parameter is the learning rate in this process, which is specified by the equation to be a rate of divergence between the input and output vectors. So slide 7 brings us to previous DBN hardware implementations. And the quest to overcome the von Neumann bottleneck and limited scalability of software-only realizations of RBMs, various hardware implementations that have been previously proposed in recent years. For example, there are conventional SRAM-based FPGAs being used. There's some work on stochastic CMOS-based designs to realize stochasticity, and other emerging technologies which are being used primarily to realize the weighted connection within the weighted array. For instance, in this table we list some RRAM and PCM recent works, which are both solid contributions. Digging further into these designs, it is seen that many of them have chosen not to focus on the optimization of the sigmoidal activation function. Thus, to the best of our knowledge, this is one of the first works herein to use a Spintronic device as a probabilistic activation function within the structure of a DBN. Nonetheless, one of the interesting works, which was published by Matti Bajnordi and Injin IPEC recently at HPCA in 2016, which received a distinguished paper, is a CMOS-based design which realizes that structure and function. It can be seen here for that each of the neurons, various area-consuming lookup tables act as pseudo-random number generators. There are some comparators, various control circuitry, and analog to digital converters utilized. Thus, even though it is the most recent and worthy work on the topic, we can see that it's utilization of many transistors to realize a single neuron. This is because, perhaps, as a community, we've been looking at this problem from the narrow and fully deterministic point of view. Thus, it's my perspective and that of the Capsule project that it may be more tractable to implement the probabilistic behavior with a device that can intrinsically exhibit the stochastic behavior, and do so in ways that can be readily modulated and controlled by a simple biasing scheme. This is what we're proposing in the first part of my talk today. With this probabilistic spin logic device that's forming our connectionist network, we're then in a position to investigate the so-called probabilistic bit, or p-bit for short, that we'll show subsequently in detail. SPI simulations indicate that leveraging this intrinsic physical characteristic using p-bits can achieve orders of magnitude energy reduction and also order of 100 times area reduction. We've covered the DBN approach, we've covered contrastive divergence to train the network, and we looked at some previous work, both CMOS and beyond CMOS DBN hardware implementations. So where we are in the talk now is to look at the circuit for the Spintronic DBN, look at the p-bit device biasing and operation, and we'll look at some benchmarks, including MNIST and energy versus accuracy trade-offs. Slide 9. So slide 9 shows the different components of the RDBN, or Resistive Deep Belief Network, and we can see drivers on the left, weights, activation function, and bias. So, having explained the basics of DBN and contrastive divergence algorithm, I'm going to start explaining about the proposed DBN structure. So, explain each one of these components, starting with the p-bit. So, the activation function is done by the p-bit device. The figure depicts the realization of a p-bit using a 3-terminal spin Hall-driven MTJ with a free layer made with a circular low-barrier nanomagnet. MTJ is part of this voltage division circuit that we see, where the voltage output is correlated with the thermal fluctuations of the circular free layer. And the CMOS inverters that are shown in the figure act to isolate and amplify the signal. The functionality of the p-bit is to produce a stochastic output whose steady-state probability is modulated by the input current in order to generate a sigmoidal activation function. For instance, a high input positive current produces a stochastic output with a high probability of 0. Meanwhile, high negative input current produces an output with a high probability of being VDD. In the absence of any input current, the device generates either 0 or VDD outputs with roughly equal probability of 0.5 for each case. And this is tunable within a range, which we'll show you on the next slide. The weighted connection is done with any type of memristive device, and what we're using here for the simulations is we use parameters from SOT-driven domain wall motion device. So during training, RWL is connected to ground. That turns off the read transistors and disconnects the read path. Meanwhile, WWL is connected to the input pulse signal that activates the write path for just an interval. During the duration of the V-pulse signal, that should be timed so that the learning rate is achieved to adjust resistance of the SOT-DWM device. So during the read operation, the write word line, WWL, is connected to ground, and the source line, SL, is in high impedance, IZ state. That disconnects the write path. Meanwhile, the read word line, RWL, for each row is connected to VDD. That turns on the read transistor for the weighted connection within each bit cell. When the input current varies through the heavy metal layer, how will that impact the output of the p-bit device? To answer that important question of device level simulation, we can obtain the p-bit behavior via the device parameter inventory in the table provided by Dr. Kamsari and data from the Purdue team. Following typical MTJ behavior depicted in the plot, there are two consistent levels created. Here the probability would be related to the input current. What can become important for the RBM would be the breadth of the current range centered around the zero magnitude current level. However, it's important to note that for the RBM, a controlled amount of random behavior can be helpful, but not completely random behavior. Rather, unpredictability can be precipitated via a lowered energy barrier and then tuned by the input current. Namely, having an energy barrier using a lowered stability nanomagnet, there can be sufficient but not an excessive likelihood of fluctuation to commute the output. On the other hand, deterministic 1 and 0 behavior would not be sufficient for an RBM to conduct its operation, knowing that it needs to learn from a complex fitness landscape of high dimensionality while avoiding becoming trapped among some local minima via exploring the landscape more fully. Therefore, a beneficial property that we can see imparted to this neuron activation function here is a tunable control over that probability in order to correlate and embed it efficiently into the training mechanism, without requiring, say, a lookup table or LFSR or A to D converter. The functionality obtained here is either a high or low resistive value coupled with only 4 transistors in total per neuron, namely 2 each per inverter, as depicted on the previous diagram. Therefore, the circuit can be a very compact building block to generate the probabilistic 1 and 0 output. By having the input current to become a control knob, either positive or negative through the heavy metal layer, would be determined by the equivalent resistance of the weighted array. So now that we have a device behavior via an underlying physical property that can conduct both thresholding and tunable randomness, we conduct a realistic circuit simulation. So that's a motif of research in Theme 4 at the architecture level, and in particular Task 6, would be to conduct circuit simulation using probabilistic spin logic in order to evaluate some trade-off at the circuit level first, and then utilize a validated circuit within a larger benchmark. Okay, herein we have a fundamental trade-off that we see in this table. This initial experiment just involved a basic circuit behavior maintaining the resistance of the fixed weight connection under varying array dimension. The citation for that resistance as an experimental result came from another group outside our project, although what's important today would be to cover the minimum probability range. So if we look at the current rated in microamps within the table, maybe that crossbar arrangement can't generate the range of input current that we're looking for. Therefore, we need to have a large enough array to create the input swing to cover the full range of probability to control the p-bit. If we're not able to access the full sigmoidal swing, then it won't attain a very tenable or even trainable behavior. The tunable range from this particular p-bit design can be narrower than others. However, that didn't really impact the operation, although we found other ways to deal with this concern, which I'll mention later. Okay, too narrow of a current range might collapse to a linear behavior as shown in the plot. So I put this table together for our talk today where I've color-coded top-level results to show some of the optimal trade-off of the parameter covered. We can see in this table within an 8x8 example,
it can only attain roughly 20% to about 80% of the desired range. But the other point that we can find here would be that the trade-off of power dissipation within the range that we're looking for. For example, in the 64 by 64 array size, we cannot see a major change in the output probability that we can cover. However, clearly the current is nearly doubled, would be a very large impact on power dissipation. Given the effect of diminishing return, selecting a 32 by 32 array would be a valid conclusion here. So the relation among input current of the activation function and resistance in a 32 by 32 array can quantify, let's say, a best case scenario of minimum energy condition for a fixed tunneling magnetoresistance ratio. We conducted a power consumption study versus area size and resistance of the weighted connection. For the 32 by 32 case from the previous slide, we changed the resistance of the weighted connections to evaluate the impact on our design. What we observe in the table confirms and also quantifies the results that we would expect to obtain, namely, in a 32 by 32 array size, with a resistance of 1 megaohm, we can attain acceptable power dissipation and increase the array size as you see in the bar graph. Again, we're depicting a trade-off between power dissipation and accuracy. In the case of the 64 by 64 array, we see by the bar chart that the power can be too significant. Of course, the preferred choice depends on the requirements of an application, but we see the nonlinear scaling impact, which we will evaluate next. As we saw how the array was designed, the highest positive currents are attained while the weighted connections are in a parallel state, i.e. lowest resistance, and the input voltages are equal to VDD, or in the negative case, connected to ground. So operationally, the key insight would be that increasing the weight corresponds to decreasing the resistance. Okay, now that we have a compact neuron device and an array circuit behavior leveraging the underlying physical property to conduct both thresholding computation and give us the needed random behavior, we evaluate it with a realistic simulation benchmark. At the application level, we ran MNIST pattern recognition task, and as we can see here, we have a 28 by 28 pixel image data. So the simplest DBN or RBM structure that we can use for this application should have 784 inputs to support all of the pixels, along with 10 outputs for 10 different classes of image, which correspond to the digits 0 through 9 inclusive. Okay, on slide 12, we continue the simulation result. We look at MNIST and also CIFAR pattern recognition applications. We've chosen some evaluation metrics for the accuracy of the design, which are the root mean squared error, RMSE that we see here, and also the error rate. So these typically follow what we would want for efficacy and accuracy. And we have a number of evaluation case studies. Here we see evaluation images. This is for the first 1,000 and the decrease in RMSE as well as decrease in error rate as defined as number of incorrect inferences divided by the number of input images. Of course, that decreases as we add more training sample. So what is the initial result? Well, we need at least 2 hidden layers here if we want to have a reasonable recognition accuracy for MNIST dataset. Of course, that's easily understandable. The more hidden layers are going to add, then the better accuracy we're going to obtain, although still overtraining can occur. So recognition accuracy versus overtraining, and the excess layer may achieve higher recognition, but at the cost of too high power dissipation. It may not be worth it. So to quantify the impact of learning as measured by the error rate, we can see how the system improves from a 36.8% error rate in a network with just 1 hidden layer and 100 frame samples down to 3.7% error rate using 3 hidden layers. As you can see here, through 5,000 training images, this is a top 1 recognition rate and average across all digit classes, although some categories like digits 3 and 8 or 5 can be lower. Generally, as we know from the typical case, that the monostroke digits, like the number 1 for instance, almost always get classified correctly. Next, to confirm the limits of an RBM generally, we move forward and try to test it with more complicated data sets, in this case CIFAR 10. What we can see in the CIFAR image set is now that we have 32 by 32 pixel images, what we're trying to do is look also with color So we have red, green, and blue. In terms of color images, we have 10 output classes: airplane, automobile, bird, so forth. And these can get kind of challenging in the case of, let's say, the difference between a car and a truck, like an automobile versus truck, as we see in the output class list, can be challenging even for a human to recognize. Basically, the simplest DBN or RBM network that we can use for this pattern recognition should have 3,072 inputs and 10 output classes. But you can see right off, we had about 90% error rate, which, if you think about it, means 0% intelligent recognition occurring, given that we have 10 categories. If we picked even randomly, we should have a 10% accuracy out of 10 classes. Now, as we increase the number of hidden layers, we can improve the accuracy somewhat, around 60%. Is that good? No, but frankly, it's too much to expect from a deep belief network such as RBM. And what we're actually focusing on right now is convolutional deep belief networks as the next step. We're getting those results with a submission to Computer Magazine using binarized version of a convolutional neural network topology. If this is of interest to you, then you can look to see our deep belief network for CIFAR application, which we'll be submitting in just a few weeks, and we're going to be posting it in the SRC pre-publications webpage. Whereas we've taken RBM to its limit and wrapping up this topic, I'd like to mention another interesting effort that has been derived from our work, and that is a simulation framework towards an automated design space exploration toolkit supporting future of p-bit and other memoristive devices. It's very important for us to evaluate beyond isolated case of a single design using a software-only simulation. So what we're interested in is to evaluate many trade-offs to get nearer to the actual hardware implementation, and that is the eventual goal of this 3-year project. To attain that goal, we've started to develop an integrated simulation framework that brings hardware into the loop.
Here we're generalizing the simulation framework to a publicly available tool called RDBN-Sim. It's a transportable framework for resistive DBNs. As seen in the block diagram, this can support a variety of tunable parameters. And the idea is that when we have MATLAB simulations, we do the training, we then map that to some now trained weights with a resistance value, then have Python codes generate the whole deep belief network, including all the capacitances, resistances, neurons, and whatever we need to implement the deep belief network. In the RDBN-Sim tool, this is all done using realistic simulations in SPICE, and nothing is operating in MATLAB for the simulation when we conduct our analysis of error rate or energy or delay. So we have SPICE models that are integrated as libraries into this framework from our collaborators from Purdue. And as listed, we have some different tunable parameters. For example, the topology of the network. You can specify the number of layers in the DBN, the number of neurons per layer, the training subset that you want to use from the entire data training set. And for weights, the idea will be to support a range of emerging devices with parameters provided for, let's say, on resistance, lowest resistance of the weight, RP in the parallel case, high to low resistance ratios, and we can readily evaluate the system impact when we change resistances of the weights. Also, a way to discretize a weight is important, and this could be automated, which we've put into the tool and are already using that. Next, for neuron activation, we may use different emerging devices for the activation function, and here we can make those automated and use different scripts to evaluate them. For example, RC circuits used to integrate neuron output. So as hardware engineers, we know MNIST technology challenges to realize the continuous weights, and sometimes we would like to make a trade-off if we're going to quantize these weights. Well, we can use these scripts to sweep through different values in SPICE and evaluate the impact. Right now we're using this tool to do noise analysis, process variation, and so forth. So some representative results that you can see that are already for specific technologies and topologies with different training images. So some representative results, which you can see in the table, would be comparing, for example, continuous weights against discrete weights. So we see here that we have infinite discrete value, which meant continuous, and we have a 20% error rate, 20.2. But what you can see that if we have a discrete factor of just 8, which gives us 9 different total resistance levels, we can have an almost comparable error rate. So this is extremely useful information at the architectural level. We want to perform what-if studies and trade-offs. And the last thing we looked at with the tool was recognition error rates versus TMR. So starting with RON of 1K ohm and looking at different TMRs, we see a big difference going from 100 to 200, so around 150. Maybe we're in that range. But to see this level off, we have to get to around 300 or 400 or so. So this allows us to go in and see that impact. And as we saw in the CIFAR 10 case, sometimes the DBN has limitations, especially with high dimensionality data, depends on the application. Some things, say natural language understanding, we may do better with alternate paradigms. And we're going to talk about one today that's biologically inspired based on stochastic spiking neuron. So I've organized this slide into 3 stages based on the stage of research. So at the first stage, we have demonstrated via simulation the stochastic spiking neuron. And the motivation for this is that from a biological point of view, neurons exhibit stochastic spiking behavior is somewhat in contrast to the leaky integrate and fire that's typically explored. There's a growing amount of evidence and literature that stochastic spiking is beneficial for brain-like computation, and there's even schools of thought that it is an essential element for learning and different elements of retrieval. So we're interested to utilize a tunable intrinsic stochasticity that exists in the p-bit to realize this so-called spintronic stochastic spiking neuron. And once we develop such a neuron, then we can begin using it in neurologically inspired circuits based on sampling theory. Neural sampling theory is a popular theory in computational neuroscience that leverages probabilistic spiking of neurons in cortically inspired circuit motifs, and these realize unsupervised learning and brain-like computation such as inference. So once the neural circuits are developed, we can start looking at more brain-inspired architectures related to the modular structure of the cortex, which shows small and large-scale modularity, such as mini-columns, macro-columns. We know that such a structure can be scalable based on biological systems, but how to implement these. Of course, we want to emphasize things like hardware efficiency. We can leverage the intrinsic properties of the available computational devices to maximize performance and minimize area, but we're also interested in emphasizing unsupervised learning where the circuits can be trained and adapt at runtime with just the inputs and maybe a reward signal, much like how the brain works. Another reason why we believe unsupervised learning in situ can be very beneficial is because we know that working with a nanoscale device, there's going to be a lot of process variation, manufacturability concerns, things with headroom and noise. So unsupervised learning can help us to adapt to such dynamic conditions. Given that motivation, let's take a look at the landscape relating biologically based and artificial connection circuits. Some interesting parallels to consider are that biological constraints can be quite similar to hardware limitations. Attributes like energy efficiency and energy density, which are fundamental for scalability and thermal budget in hardware design, can be somewhat analogous to, let's say, the amount of nourishment needed to sustain an ion pump transport across the plasma membrane. So hardware designers, on the other hand, have a limited area budget and limited number of metal layers for routing on a chip, while at a component level, biological brains exhibit innovative approaches to maximize their surface area within their volume constraint. Biological systems operate effectively despite noisy input information and rely heavily on imprecise and imperfect components, which of course is a looming challenge in the post-CMOS era. Well, nonetheless, biological systems can sustain their computational viability with such noisy inputs, and we see this happen with their spiking hardware. So some current approaches that's been investigated for spiking neural hardware include custom silicon such as IBM's True North. The Human Brain Project has produced a couple of different architectures as well. There's many more spiking neural ASICs that have been developed, as well as FPGAs, some exploratory systems that also use emerging devices. These include some Spintronic-based, memristor-based, and even phase change memory was designed. So this is a big space. There's a lot of good work that's done here over many decades. Thus, what specifically am I advocating here in this section that we talk about today, trying to improve? Well, a worthy trend that we really want to hone in on here is leveraging the biologically ubiquitous stochastic switching behavior. That is one whereby the spin-based devices that we've been discussing so far today we can see perfectly relate to this property. Additionally, the transition from circuit level to architecture level, I think, is an underexplored area, attempting to translate some of the most useful strategies of aggregation approaches that exhibit biological realism. So I'm going to talk about that on the next slide. Previously, when stochasticity was introduced, it typically required large integrated circuits that involved pseudo-random number generators, like linear feedback shift register, while our approach uses a straightforward compact circuit shown here in this neuron circuit, which we'll go over in the later slides. And with such circuit, we can develop more compact and efficient modular circuits to leverage both spin generating and consensus coupling or consensus forming capabilities. These are what we're examining as interesting and offer very high speed, actually ultra high speed, mimics for a neuron in an unsupervised learning framework. I identified that as comprising one stage in the previous slide that we saw was simulated in stage 1. We have results for those and some recent publications which I'll overview next. To extend to brain-like computations, namely at the circuit architecture level, that would be stages 2 and 3 on the previous side. Thus, we can leverage the broad idea of cortical aggregation to explore pathways towards some of these aspects of cortex-like capabilities in silicon. So as mentioned previously, we can consider 3-terminal or 2-terminal MTJ-driven p-bit devices. Now let's look in more detail at the 3-terminal MTJ-based design which we developed, and it was evaluated to generate a stochastic spiking neuron, or S3N. And then after that, we can go into detail in the following slides. So in terms of attributes, the S3N utilizes spin Hall effect-driven p-bit. It operates at a very high speed, low energy per spike, and most interestingly for our purposes is that the spike rate is determined by the input current. Next, we've extended spin-based spiking neuron to voltage-controlled version as shown here. And it's pretty similar to previous design, except that it uses a voltage-controlled p-bit, as we see here, and that allows the spiking rate to be controlled by an input voltage instead of current. So what we've been currently exploring using these devices is how to realize biologically inspired, in situ unsupervised learning, and do that with a hardware efficient design. We call that the neural sampling core, or NSC. Some interesting characteristics of the NSC, which we'll dive into a little bit, is it's asynchronous. It uses a binary synapse. It has probabilistic learning rules, and the unsupervised learning is activity dependent on Hebbian learning. The catchphrase for Hebbian learning, those that fire together wire together, and we try to realize that here. So it's a work in progress, but we have some preliminary results that I'll show you. So some current directions we're going to explore include extending the NSC, or neural sampling core, to include recurrent excitatory connections here, as well as a separate pool of inhibitory neurons for temporal pattern recognition. We also want to explore the modularity of recurrent NSC in order to hierarchically organize somewhat deep spiking neural architecture, and we'll show a little more as we go forward in that. And finally, in a slightly orthogonal direction, we want to explore if we can leverage the p-bit to improve the activation function of XNOR, resistive crossbars, which are used in recent binary deep neural network research. Here we have the spin Hall effect-driven p-bit, which was developed by Professor Data via our collaborators at Purdue, that utilizes thermal noise within a low energy barrier MTJ structure, such as just a few kT, to provide tunable stochasticity.
whereby the probability of the MTJ being in a parallel or antiparallel state excuse me, is adjusted via input current, as shown on the plots earlier that we saw. It follows a sigmoidal behavior as given by the voltage dividing equivalent circuit. So how can we leverage this circuit to realize stochastic spiking neuron? Distinct asynchronous spikes, which, as is demonstrated here, you can see that the magnetization, which is shown in blue, randomly jumps from the two possible states according to the input current and the time average magnetization, which is shown with the red line. And that follows the sigmoidal behavior. So with these capabilities in mind, we considered how we could leverage such a device to realize a stochastic spiking neuron with distinct advantages of asynchronous spikes via electrically tunable spike rate. So that is how it can be done with a current-driven device. Now let's take a look at the circuit operation. To quickly describe how the device operates, we identified in a previous slide that based on input current, the p-bit will probabilistically be in a 1 or a 0 state, which will either charge or discharge the node Vmem. If the p-bit is in a 1 state, enough that Vmem would reach the threshold in the inverter, then spike out will go high, and subsequently turns on M0, charging Vmem. The spikes are on the order of 2 gate delays, so 10 to 12 picoseconds nominal. Power dissipation of the circuit was evaluated to be from 1/10 of a microwatt up to 10 microwatts, 9.6. Depending on the spike rate, maximum spike rate can go as high as 8 spikes per nanosecond, and that can be achieved on the order of only 1 femtojoule energy per spike. As you can see how the device operates here at the bottom, we increase the input current in a stepwise fashion, which then biases the magnetization of the free layer increasingly to the antiparallel state, which then causes Vmem to charge more and more, and whenever it reaches the threshold of the inverter, a spike is produced, and Vmem is discharged some amount. So when comparing the S3N to previous spiking neuron implementations, the main distinctions to note is how various digital CMOS designs require large pseudo-RAM number generator circuits, greatly increased device count, and previous implementations using emerging devices typically require some type of reset cycle, for example, a write-read reset cycle, whereas our approach provides the spiking behavior intrinsically. So we see digital CMOS using the pseudo-RAM number generator, and we see two that require write-read reset cycling. First, the hybrid CMOS memristor, and also hybrid CMOS been designed. There was one by Lian Gandara. Additionally, our approach operates orders of magnitude higher speed and lower energy compared to these approaches. And some of those parameters are listed in the table. You can see our source of stochasticity is thermal energy, the intrinsic behavior for spike implementation, which is our real advantage, and 10 picosecond spike time, about a femtojoule energy. And the cell area is comparable or less compared to these existing designs. So now we're going to quickly go over the voltage-controlled S3N design. It's quite similar to the current control design, except that it uses the embedded p-bit proposed by Purdue. The embedded p-bit uses a standard 1T, 1 MTJ structure with a low energy barrier MTJ. Again, the output voltage has a probability to be in a high or low state, which follows a sigmoidal behavior based on the input voltage shown here. If you'd like to know more details about how this p-bit works, you can take a look at our collaborators' papers, which they have a recent one electron device letters that shows this circuit operation in detail. So the voltage-controlled S3N basically utilizes the same scheme of charging a membrane voltage based on the state of the embedded p-bit. And once the membrane voltage reaches the threshold of the inverter, the spike signal goes high, which discharges the membrane voltage, providing the spike power comparable to the current-based design. As we've shown here, an input voltage of about half a volt, 550 millivolts, produces the maximum spiking rate, while a voltage below
330 millivolts provides pretty much no spiking, and the spike rate follows a sigmoidal behavior. We don't have a paper yet for this design, but we're looking to use this version going forward because voltage-controlled input is much more attractive than a static current-controlled input for energy. Of course, our collaborators' research and design and fabrication of p-bits, we can update the S3 design with these future iterations of the device. Basically, we need a probabilistic switching binary voltage, which is all that's really needed in this case, that we get from either of these designs. To utilize these spiking neurons, we're primarily focused on the neural sampling theory, which is a popular theory in computational neuroscience based on Boltzmann's work, which they had demonstrated that networks of stochastic spiking neurons implement Bayesian inference, and that was later extended by Langston to work with Hebbian learning in a soft winner-take-all network, which are just feed-forward networks, as shown here, where the output neurons inhibit each other in such a way that when one spikes, the other neurons are unlikely to spike, but are not forced to spike. In this case, the Hebbian learning from soft winner-take-all generative models of the interdistribution arise from expectation maximization of a machine learning process for unsupervised learning that typically requires 2 iterative steps. These are approximated in online fashion for spiking neural nets. The expectation step, or E step, that's basically a guess as to what the hidden causes are of the output. And in neural sampling, this correlates to an output of the neuron spike. The maximization step, or M step, is a way to improve the guess until a local max is reached in the log likelihood of the generative model. In these spiking networks, that correlates to spike timing dependent plasticity of the synaptic weight update. So we aren't really setting out to replicate their work here directly in hardware, but we're using that as a guide for how we realize a similar behavior in a hardware efficient manner. What we've come up with so far for this neural sampling core, where very briefly, each one of these yellow squares is a synapse and each one of these blue squares is S3N with the required associated hardware, and the green and red squares basically monitor the activity of the pre and post neurons for unsupervised learning updates, which we'll show detail now. So some characteristics that we're targeting is for the core to be hardware efficient as we can, using binary weights, probabilistic learning rules that cover the stochastic switching for spintronic memory devices, as well as trying to minimize area of each synapse, since that'll take up the bulk of the circuitry area. In our present design, when operating normally, it's asynchronous but mimic to biologically neural network, and can leverage the temporal correlation of spikes, which doesn't need a clock and the associated power delays. The design is an orders of magnitude faster than its biological counterpart with a rapid 10 picosecond pipe, and compared to 1 millisecond order for typical biological neuron. It displays characteristics similar to those in biology, such as how each spike induces a double exponential. As we see here, voltage trace as the one shown. That's similar to biology and in line with neural sampling. The core has a low energy per spike, and leveraging the probabilistic regime of the Spintronic device, we can reduce the symplectic energy update compared to deterministic approach. And at the core, we've demonstrated unsupervised learning with a 2-phase approach, where the first phase is the inference phase and presents an input to the core, and the core is allowed to run normally for a short period of time, and the activity of the pre and post neurons is monitored. And then during phase 2, the update phase, based on the neuron activity, will probabilistically potentiate or depress the synapse. So as illustrated here, we see the different test patterns, and they're presented for 2 nanoseconds each, and then the network is updated before the next test pattern is introduced. It's good to also emphasize that this is work in progress and the details are still being tweaked, but we'll show some preliminary results. So now we're getting to the detail of different components of the neural sampling core as they stand today. The neural circuit is based around the voltage-controlled S3N p-bit neuron described earlier, along with the current mirror. Based second-order low-pass filter, which is translating the spikes into the alpha-shaped post-syntactic neuron. And the potentials shown here are for the two branches. We see one excitatory input and one inhibitory input. So the synapse we're currently investigating leverages the differential spin Hall MRAM, and it's convenient for us because of simulation. Here we're using complementary switching, and we see here one MTJ is in the high state and one would be in the low state because we always have this complementary behavior. That helps us with a larger voltage swing when it's used as a voltage divider. But we're also investigating alternative designs, as we mentioned, and how the circuit works is if the brief spike comes in, that the corresponding brief voltage occurs on the NMOS, which causes a brief current draw in the current mirror, charging the potential of the input, and a similar approach is used for the inhibitory branch. Now the synapse is updated based on the post activity, which determines the synapse is updated or not. The pre-activity, which determines this being strengthened or weakened. The activity signals that we're going to update are determined by that circuit, whereas in the previous inference phase, the research circuit was pulsed by turning on this PMOS. So the input voltage to the inverter. So here we see that during the inference phase, each brief spike pulls down the voltage. If enough spikes are generated, and the voltage crosses the barrier, and this threshold is sufficient to turn on the inverter. So activity signal goes high for the update phase. For a 2 nanosecond inference, we found that threshold of 3 spikes is enough, and we can adjust this capacitor to account for that value. So the exact details of how long the update should be and the precise amount to apply right now is still under investigation. Some interesting results we've attained so far with our simulation framework, which consists of using HSpice to model the circuits and obtain the characteristics, and then model these in Brian 2, which is our spiking neural network simulator that we're using, publicly available. It uses differential equations to do that. We've tested the system using vertical and horizontal bars as test cases. These provide some visual clarity of how the network learns. We see a 20 by 20 pixel input window, where a blank pixel indicates an input with a high rate of spikes, and each white pixel here is a low rate of spike. Each of the 40 possible pixel bars that we're looking at here is presented one at a time before the input phase. So in our studies, we've seen that a 10% depression of 5% works quite well. So each one of these squares is representing the receptive field of one output neuron. That basically means where there's a dot, there's a high input synapse, and the neuron will respond to that input. The system is initialized here to be completely random, but during learning, there's a lot of jumping around. Each input neuron tends to settle into recognizing one of 3 different input patterns. After learning, we have a group of neurons that can recognize the specific patterns using unsupervised learning. Our next steps are to evaluate the performance of the network using MNIST and raw pixel values using extracted features such as the histogram of orient gradients. So a couple of the future directions that we have planned include extending the neural sampling core to include recurrent excitatory conditions as well as inhibitory neurons, which is more akin to cortical modules and can enable temporal pattern recognition. We then like to integrate such cores to organize these into a more deep, hierarchical, spiking neural, multisensory type of a cortex design. In an orthogonal direction, we believe that we can implement new improvements for binary deep neural networks using the p-bit. We have that going on right now. I'll mention a paper that we're composing on that. And as mentioned, stochastic binarization is more appealing for for implementing the sign function, but it's harder to implement for hardware to generate random bits. So we're going to take advantage of that in this current paper that we're working on now. as opposed to most approaches that use a deterministic sign function, but we're going to try to use the p-bit to generate that. And we'd like to mention that this work is also complementary with other E2 CDA efforts, in particular Jason CO at ASU, and others are using some XNOR RRAM based arrays for the memoristic weight.
So at the end, I'd like to go through some manuscripts if we have time, and we're at a few minutes, so I'll go over these very quickly. These are manuscripts we have in the SRC library. If you look, this was a International Conference on Rebooting Computing, IEEE conference. I presented this paper where we've added the p-bit to the reconfigurable fabric of heterogeneous technology fabric. And the idea here is to have different types of computation supported, both deterministic and probabilistic, on a programmable fabric. Next paper that we had goes over the second part of the talk today when we went into spiky neural net, and there's full details there. That paper is a preprint. It's also available on SRC. And we're finishing the computer paper, which was the last one I mentioned, on the XNOR array and the binarized version. We also had a paper that presented, which was the first half, a lot of the first half of this talk, related to the GLS VLSI paper, which was the RDBN, and that was all on the Boltzmann machine. Then we have a paper in review right now, which is going further than that and looking a little bit more at the design tool and the simulation framework that we talked about. And we also have a paper in review to IEEE rebooting this year, which is looking at the training process and training the loop in the hardware versus using MATLAB to generate the weights, which what most people are doing right now, but may not be practical if we think about from a process variation point of view. When this hardware is actually fabricated, we really need to train in situ. And I think this is an area that a lot of good work needs to be done. There hasn't been a lot by the community to really look at this issue yet.